So we have already dealt with the Fourier series, right? In the last week, so eighth week was almost. I guess week seven also was related to Fourier series also, and there we just read about like how can you, if you have been given a power signal or a periodic signal, how generally you write it as a. As you know that any signals, any power signals that you have dealt as of now, or the periodic signal that you call, you can write it in the form of some sinusoidal, right? But there is some constant that you were having, the frequency or the omega that you were using in the sinusoidal, any signal that you were can be made or the combination of some sinusoidal, there the frequency or the omega was in the form of some discrete value, right? So whenever you were adding a number of n numbers of sinusoidal curves, then you were getting some power signal, right? Any power signal can be written in the form of some sinusoidal curve, but there the omega or the frequency were some discrete, like a fixed number of or different sets of frequency was there. In the Fourier series, so here whenever you have energy signal, right, those are not periodic, okay, so those you are not able to write it as a combination of sinusoidal, right? So for those cases where you have a energy signal or a bounded signal, sort of energy signals, non-periodic signals, so there the Fourier series concept will help you, okay, and Fourier series, Fourier transforms will help you to, for any signal that is in the time domain, you can just write it in the form of a frequency domain with the help of this transform. Maybe we'll read about the Laplace also in the coming week, but as of now, we'll just deal with the Fourier transform. So the formula almost, not normally you write it as the Fourier transform of any signal xt is written in the form of omega, and that will help you like whenever, so any signal that is in the time domain, you want to read that about that signal, and that will help you a lot whenever you will deal with the circuit, right? So you already know that when you transient, like in the transient analysis, when you do that, Laplace help a lot, right? The technicality, if you don't want to go into much like in the time domain, maybe many a times you get confused, right? How does the capacitor or the inductor behave? But whenever you change that into a Laplace domain, it becomes very simple, right? And then from the Laplace you can again come back to the like the time domain by taking the inverse of that, right? And then your circuit analysis becomes very simple, right? So similarly, Fourier transforms also, you can analyze any signals that is there in the time domain, in the frequency domain, and that again will help you a lot in analyzing those signals, right? So the Fourier transform that you do, and these are the mostly the energy signals, okay. So how do you calculate? So this is how generally you calculate the Fourier transform of any signal. Or minus a omega t dt. Are you able to hear me, and you can see my screen, right? The voices and all is fine, right? You can hear
Yes,
me.
sir.
Okay. Okay. So this is how generally you write the Fourier transform on Fourier transform of any signal, and mostly the energy signal you do. Like for the energy signal, for the power signal, you already know that you have to calculate the inverse of that signal, right? So how do you calculate the inverse? So Fourier transforms inverse. These are the basic formulas to calculate, and we'll see also how to calculate the Fourier series of any signal. 1 by 2 pi minus infinite to infinite. So as I explained to you, this is how generally you calculate the Fourier transform. And if you have to calculate the inverse of if any signal that has been given in the omega domain, right, frequency domain, to get in the time domain, you take the inverse of that signal that has been given in frequency domain, and this is how generally you calculate the inverse Fourier transform. Okay, and that is basically defined for the energy signal. There are some exceptions, like for example, for the delta signal. For the delta signal, also you can calculate the Fourier transform. Okay, mostly whenever you want to calculate for the power signal, right, generally with the help of the formula doesn't work. With the help of some approximation and all, we generally we do, like in Fourier series we have seen that, right? Now generally you change how generally any power signal generally is the, you can write it in the form of some sinusoidal, okay, and Fourier transform you can't calculate for any signal that is neither energy neither or nor power. Okay, so that you can't do. But here we'll just be mostly we'll be just dealing with the delta is the exception, but otherwise we'll be calculating the Fourier transform for energy signals. Okay, let's for example if you have to calculate, this is a formula and mostly it will rotate around this formula itself. If you just let's for example let's start with one example. If you have to calculate the Fourier transform of an energy signal e to the power AT ut, will you be able to calculate for this signal e to the power AT ut? Is this an energy signal? What will the plot of this e to the power AT ut? This is how it will go, right? So for this you can't calculate. This is not an energy signal, right? So for this it's not possible. Are you able to get it? Is my voice? It's not clear or what? Like I guess some people are saying it's breaking a lot. Is it breaking a lot?
From my side, sir, it's clear.
Okay. Okay. So please let me know whenever if you feel like you're not able to hear me, then maybe I'll change my Wi-Fi connection. Okay. So this signal I told you this is not an energy signal, so you'll not be able to calculate the Fourier transform. Correct. Let's go to the next signal. If you have to calculate, and this is one of the exception, right? Delta t so is like one of the exception I told you. If you have to calculate the Fourier transform of a delta signal, how will you calculate? This is xt, right? What is the formula? Generally, how do you calculate a Fourier transform of any signal xt? Minus infinite to infinite xt e to the power minus j omega t dt. So xt you just put the delta function here, minus infinite to infinite delta t e to the power minus j omega t dt. What will be the integration for this function? X, this function e to the power minus j omega t at t equals to 0, right? Because delta is defined here at t equals to 0, right? So this will be equals to 1. So for a delta function, the Fourier transform is 1. Okay. So for a delta function, I told you the Fourier transform is 1. So the delta function was like this, the Fourier transform. So this is in the time domain, this is in the frequency domain. Okay, in the Fourier series we have already studied, right? Whenever you write any equation, any periodic signal as a combination of sinusoidal curves, you deal with some coefficient and all, right? And then you have already read that you just combine some of the frequencies. So those the signal Fourier series that you get generally is in the form of some discrete, right? But here the Fourier transform that you are calculating mostly for the energy signals are continuous. Okay, for the combination of n number of signals, like n number for each of the values of the frequencies, you will be having some value. Okay, so here you are getting a continuous signal in the Fourier, like in the omega domain, or you can say in the frequency domain. But in the Fourier series, what you were getting, it was you were getting some sort of a discrete, like combination of some of the omega's value or some of the frequencies value. Okay. Now, if you have to calculate 10 बजे. Okay. So now the third problem. So we have dealt with so and whichever like signals that we will be calculating the Fourier transform, it should be like most of the signals are very standard signals. So you can just remember the Fourier transform for each of the signals, and that will help you also to directly, because these signals mostly will not be asked. With the help of this and when we'll deal with the properties mostly will help you to calculate for different types of a signal, like a different difficult signals. These are very basic signal. Let's, for example, you have to calculate the Fourier transform of e to the power minus at ut. Okay, this is a bounded signal, energy signal, so you can calculate the Fourier transform for this signal, right? How do generally you represent this signal? This is how it goes, right? E to the power minus at ut. So you can calculate the Fourier transform for this signal. Okay, so we were not able to calculate for this signal, right? E to the power 80 ut, right? This was not bounded, neither energy nor power signal. So we are not able to calculate the Fourier transform for that signal. Okay, but here we are able to calculate the Fourier transform for this signal. As you can see that this is the energy signal. The area also is like you can calculate, it's integrable. So you can calculate the Fourier series, Fourier transform for this signal. Okay, so how will you calculate minus infinite to the power minus 80 ut and then e to the power minus j omega t. Correct. So this is what dt. So it will be defined from 0 to infinite e to the power minus 80 e to the power minus j omega t, because you have ut, so it will be defined from 0 to infinite dt. So you'll be having e to the power minus t a plus j omega, right? 0 to infinite dt. So e to the power minus t a plus j omega minus a plus j omega. Just put the value 0 and infinite. We'll be getting 1 upon a plus j omega. So for a signal e to the power minus 80 ut, you have a Fourier transform a plus j omega. Okay, is this clear till now to everyone?
Yes, sir.
Okay. So we have calculated for two signals now. You already know that for xt we have Fourier transform xw in the frequency domain. So we have calculated for delta function. Delta function we got 1, and for e to the power minus 80 ut we got the Fourier transform as a plus j omega. Correct? Okay. So this was our, for this signal xt, our Fourier transform. We got this, right? So generally we deal with the magnitude spectrum and the phase spectrum. Okay. So for any signals which are in the frequency domain, let's for example the signal, right, s omega equals to 1 upon a plus j omega. If you will calculate the magnitude of spectrum, you have to calculate the magnitude. If you will calculate the magnitude of the signal, what are we getting? 1 upon, and if you have to calculate the phase what will you get? Minus tan inverse omega upon a. Can you tell me whether this signal is a, this magnitude of spectrum that you got is even or odd? If you'll just replace x omega with minus omega, you'll be getting the same signal, right? So this is a even, right? And this will get it for all, like always you'll be getting for all the real signals. You'll always be getting the magnitude of spectrum as a real, like as a even signal. And for the phase, so if you just want to, this phase, right? So this is magnitude of spectrum. For all the real signals, you'll always be getting the even magnitude spectrum. And the phase spectrum, if you'll just replace omega with minus omega, what will you get? This will always be odd. Okay. So for any real signal, you'll always be getting the magnitude spectrum as an even signal. Okay. And the odd, the phase spectrum as the odd. You can check it, right? What is the basic properties of any even signals? The mirror image of, how do you check if you have been given a graph How do you check whether the signal is even or odd?
Symmetric about the y-axis. Even signal is symmetric about y-axis.
Yeah, this is symmetric about y-axis, and this is about origin. I hope you're able to know. Right. Okay. Now, so these are very basic signals. So the signals was one exponential signal, the very standard signal. Now we have to calculate the Fourier transform for a rectangular function. I hope you remember the rectangular function, right? How do you represent this rectangular function? From minus half to half, correct? The magnitude was 1. So now we have to calculate the Fourier transform of this rectangular function, right? This is also energy signal. You can simply calculate the Fourier transform for this signal, right? How do you calculate that? How will you calculate? So the formula you already know, xt minus infinite to infinite e to the power minus j omega t dt. Here also the signal is what? The signal is 1. So you have 1. You have to integrate it from minus half to half e to the power minus j omega t dt. Correct? What will you get? E to the power minus j omega t upon minus j omega minus half and half. If you'll write it, what will you get? 1 by minus j omega e to the power minus j omega by 2 minus e to the power j omega by 2. Correct? Now, if you will do that, let's for example, you are just this 2 if you are multiplying here, 2 if you will multiply here. So this signal here j is there, right? So if j comes here, so you can just delete the j here, and you will multiply the minus, so you'll be left with 2 upon omega e to the power j omega by 2 minus e to the power minus j omega by 2 by 2j. What is this signal? Correct. So this is sine omega by 2, and this also you can write it as omega by 2. Do you know what is this signal? If you are writing any signal sine t by t, what is this signal? Have you heard of sinc function? No, no, this is not. Have you heard of any signal sinc? No.
Yes,
Right. So how do you represent a sinc function?
the sine t upon t.
Sine pi t upon t. Pi t. Correct. This is the sinc function. Okay. How do you represent a sinc function? Sinc function is what? Sine pi t by pi t. Sine t by t is a sampling function. Okay. So here, if you have to represent this in the form of a sinc, how will you represent? You already know that sine pi by t upon pi t is the sinc function. Correct? So I want to represent this sine omega by 2 upon omega by 2 in a form of a, see this you can directly represent with the help of a sampling function. With I want to write it in the form of sinc function. Why do we want to write it in the form of a sinc function? You will see that many a times many of the signals in the Fourier transform, you will get to know that those are represented in the form of a sinc function. So the transform of any signal will be represented in the form of a sinc function. So see, sinc function generally is represented like this. Will be a This is how generally you represent a sinc function. Okay, and these are the multiple like 1, 2, 3, 4, something like that. This is how you represent a sinc function. So if I want to represent this sine omega, so already we know that for any rectangular function, your the Fourier transform that you have calculated is in the form of sine of omega by 2 upon omega by 2. Okay, this is some form of a sinc function. Okay, this is like sinc of omega by 2 pi. Is it clear to everyone or not?
Yes.
Everyone understood, right? So whenever, if you have been any a times, if you have been asked to calculate for a rectangular function the Fourier transform, what is the Fourier transform of a rectangular function? A sinc function of omega by 2 pi. If it is in the form of a omega, if it is in the form of a frequency f, then it will change, like you already know that, right? 2 pi f is what? Omega, so it will change accordingly. But mostly whenever in the Fourier transform, if you will dealing, 99% of times it will be represented everything in the form of a omega only. Okay, so for any rectangular function, see, if, one second, if we have a rectangular function a of rect, what is the plot of this function t upon tau? How do you represent this? This is a and this is minus tau by 2 and this is tau o 2. So here whatever has been represented is the width of a signal, rectangular function. Okay, so here it was 1, right? So it was minus half to half, and a was also 1. So this is what we have represented as a width of a signal. Okay, so here it was 1, right? So it was minus half to half, and a was also 1. So this is what we have represented as a width of a signal. Okay, so this is what we have represented as a width of a signal. Okay, so this is what we have represented as a width of a signal. Okay, can you hear me now? Sorry, I just lost the connection. Okay. So till sync we have discussed, right? So I told you. So till now we have seen for three standard signal, right? So for delta function, we saw that the Fourier transform is 1. For e to the power minus 80 ut, we saw that the Fourier transform that we got was a upon a plus j omega. So the first signal, second signal, and third signal is for any rectangular signal, we are getting a sinc function as a Fourier transform. Okay. So I hope up till now it is clear, right? And I already told you, right? Any sinc function will be represented like this, right? This is how generally it is represented. Whenever you are writing in the form of sinc function, right? So this is like the t will represent, the t is generally equals to the integers. So here the t equals to 1, here is 2, 3, 4, and here it is minus 1, minus 2. Okay. So why? Because you already know that sinc function is what? Sine of pi t upon pi t. So if the t equals to 1, so the first time the sine of pi becomes 0, right? Similarly, sine 2 pi will become 0 at this place. So this is how it goes. Okay. So now, so we have dealt with 2, 3. At least you now know how to calculate with the help of the formula. At least how to calculate the Fourier transform, right? So this is done, and I already told you that in the for the Fourier transform, in the Laplace, in the frequency domain or in the omega domain, you will be getting a continuous signal, right? That was not the case for the Fourier series; that was discrete. Okay, here you are getting a continuous signal. Okay, in the omega domain. Okay, now let's deal with some of the properties that will also help you. So the properties of the Fourier transform generally will help you to calculate the Fourier transform of most of the signal. Even a difficult signal you will be able to calculate with the help of the properties of the signal. Okay, and there are some, like I already told you, there are some like limitation also for the Fourier transform. I already, like, the signals would be absolutely integrable. That the signals would be energy signal. For the energy signal, you can directly calculate. There's no problem in calculating the formula that we know already. You can directly use it for the energy signal. Okay. See, for the power signal, directly you can't use the formula. Okay, there are some approximation that generally we do that we'll get to know, but at least for now, you must be you should be knowing that for the energy signal, you'll be simply directly the formula that we have used. You can directly use the formula to calculate the from the time domain. You can get into the omega domain or the frequency domain for any of the energy signal, right? Okay, so let's deal with the some first property. So the properties are pretty similar to the one that we have dealt as of now for the Fourier series also. So the first properties is the signal, like if you have, the first one is the linearity properties. It's like same as for x1t, if you have the Fourier transform as x omega, and for x2t, if you have the Fourier transform as x2. So if you have been asked to calculate for a x1 times plus b x2 times, so we'll be getting a x1 omega plus b x2 omega. Okay. So now if I'm asking you, so can you just solve this? So solve. So 3 to the power e to the power minus 80 ut minus 5 rect function. So you already know that for exponential decaying function, what is the Fourier transform? For a rect function also you already know uh, the Fourier transform. Okay, directly you can. So 3 times. So you already, what is the Fourier transform from e to the power minus 80 ut? A plus j omega. Correct? Right? And for this rectangle function also you already know 5 times sine of omega by 2 pi. Correct? So this is how generally you calculate if you have been given a combination of different signals in the time domain, and for each of the signals, if you know the Fourier transform, directly you can calculate the Fourier transform for the whole signal itself. Okay, now the second property is same to, we have dealt this property is also the time shifting, right? So let's, for example, for xt, if you have the Fourier transform x of omega, so for x of t plus minus t naught, you can calculate you'll be having. So if you are doing the time shifting in time domain, right? If you're doing like that, this happens if you do the, let's for example, if you are doing the shifting, time shifting in time domain. So normally you will multiply a complex value e to the power minus j omega t naught. So if you are doing plus minus, so it will be plus minus, so it will be plus minus itself. Okay. So for x of t minus t naught, we'll be multiplying x omega times e to the power minus j omega t naught. Now for x of t plus, if you are just shifting, delaying the signal, x of omega e to the power j omega t. And this happens like you have already seen the similar property in the series also. So and see, for the frequency shifting, if you are doing the frequency shifting means the next property is frequency shifting. Here what happens, let's for example you have a signal xt. For xt you have a Fourier transform as x omega, right? And if, let's for example, if you are multiplying something, multiplying exponential component x omega naught t, so what will happen, there will be a shift in frequency. So here it is plus, so it will be minus here. So it's pretty simple. Like in, so the time shifting and frequency shifting, like it's like in, if you are doing a time shifting or if you are shifting in one domain, you will have to multiply the exponent, the component, like the complex e to the power minus j omega or e to the power j omega t naught in the other domain. So here, if you are shifting in time domain, you are multiplying that complex value in the frequency domain, right? So here, if you are multiplying something like the complex value in the time domain, then you are shifting in the omega domain, right? So this is how it works. If you are shifting anything in the like the frequency any one domain, then you will have to multiply a complex e to the power j omega t naught in the other domain. Okay, this is how it works. So it's pretty simple to remember also. I hope this is clear, right? Is it clear? So shifting in one domain is generally multiplication of complex exponential in other domain. Okay. So now I'm giving you some example. If you have to, so now solve some of the. So you know, for a rect function, you are getting a sinc function. Now, if I am shifting t minus t naught, what will I get? E to the power minus j omega t naught times sinc function. Correct? If, let's for example, I am multiplying e to the power minus at ut, I was having what? 1 upon a plus j omega. Now I am multiplying something, let's for example, I am shifting e to the power minus a t minus t naught, u of t minus t naught. So what will happen here? So if I am doing shifting in time domain, what will happen here in the frequency domain? The complex exponential multiplication, right? So 1 upon a plus j omega to the power minus j omega t naught. Is it clear to everyone? Yeah. So now you already know that for a delta function, what is the frequency transform? 1. If I am doing d of t minus t naught, what will happen here? What will be the frequency? What will be the Fourier transform for this del of t minus t naught?
e power minus j omega t.
Correct. E to the power minus j omega. Correct. Now, for a rect function, you already know. If I am multiplying in the rect function, e to the power plus j omega naught t. What will happen here? In the sinc function, what will happen? Omega minus omega naught upon 2 pi. Correct? Making sense, right? So these are some of the properties. So next property is the time scaling. If for a signal xt, if you have a Fourier transform x omega, right? So for x of at, you'll be getting the Fourier transform as 1 upon mod a x of omega upon. So wherever there's a multiplication of some constant a times t, right? The scaling of t will be dividing each of the frequency with omega, okay, and even the magnitude also with a. So for xt you have x omega, right? So for x of 3t you will be having 1 upon 3 x of omega by 3. Similarly, let's for example if you have x of minus t, what will you get? Can somebody tell me? For x of t you already know that x of omega. What do you get for x of minus t?
X of minus omega.
Correct. So this also is time reversal properties. So if you know for xt, you can calculate the Fourier transform for x of minus t. Okay, you just have to replace the omega with minus omega. Time reversal property. Now you already know that for this signal e to the power minus at ut. What is the Fourier transform for e to the power minus at ut?
1 by a plus g omega.
Correct. 1 upon a plus j omega. So what will be the Fourier transform for the signal? E to the power at u of minus t.
1 1 1 by a minus g omega.
Correct. Hmm. So now if I'm asking you for this signal e to the power minus a of mod t, what can I do? Can I add both 1 and 2? Linearity property, right? You can use it. If you know the Fourier transform for one signal and the other signal, if you have been asked to calculate the Fourier transform or the summation of those two, you can directly add the Fourier transform also. So 1 upon a plus j omega plus 1 upon a minus j omega. Correct? We will be getting 2a upon a square plus omega square. Correct? The Fourier transform for e to the power minus at ut is 1 upon a plus j omega e to the power minus a mod t. You have a Fourier transform as 2a upon a square plus omega square. Correct? Clear to everyone? Okay. So as of now, how many signal we have seen? Del of t, the Fourier transform is 1. E to the power minus a t ut. The Fourier transform is 1 upon a plus j omega. Why am I writing so many times? So that all the standard formula, all the standard function you should be remembering. And with the help of this signals only, you will be able to calculate most of the Fourier transform. Okay, and again for a rect function, we'll be having a sinc function, sinc of omega by 2 pi, and e to the power minus a of mod t, we'll be having Fourier transform as a square plus omega square. Okay, so we have up till now we have read 4 standard signal. Now the next property is the time differentiation property. This property is also you would have read many times. So what happens here? If for xt you have a Fourier transform as x of omega, if you are differentiating, so what will happen? J omega will get multiplied here. Okay, or one more thing, the frequency differentiation. For xt you have x omega. Let's for example you have been asked to calculate for x t is multiplied, right? So what will happen? J you will be multiplying and d of x omega. Okay. So here also differentiating in any domain. So what is happening if you are differentiating in one domain, in the other domain you are doing the multiplication of a variable in the other domain. Let's for example here you were differentiating. So you'll multiply the variable. What is the variable here? Omega. Okay. So if you are differentiating in here omega, so j you first j is multiplied whenever you are writing in the omega domain, you'll be multiplying the j. Okay. The thing that you should be remembering is differentiating in any domain is normally multiplication of variable in other domain. Okay, so you're differentiating here, you're multiplying the a variable omega here. Okay, so here differentiating here, multiplying the domain variable that is t here. Okay, I hope this will help you to remember. So you can just remember the time differentiation and frequency differentiation, or and the other one was the time shifting and the frequency shifting. Okay, so you can just remember. This is pretty simple to remember. The other was shifting in any domain, and what was happening? Multiplication of complex exponential in other domain. Correct? Now, one more thing. So, as of now, we have dealt with some 6, 7 properties. Now, the other one is, so how do you write x of omega? You write it as what? Minus infinite to infinite x of t to the power minus j omega or t dt. Now, let's for example, if I am putting omega equals to 0. So, if you have been asked to calculate x of 0, do you know what will happen? So x of 0, if you will calculate, you just put omega equals to 0, what will happen? Minus infinite to infinite x of t dt. That means what? If you have been asked to calculate the area of any signal in time domain, what can you do? You can just calculate the Fourier transform and check for the value at x omega equals to 0. Whatever the value that you are getting, that will be the integration of that signal in t domain. Correct? Similarly, what will happen if you have been asked xt, you can write it as what? 1 by 2 pi minus infinite to infinite x of omega e to the power j omega no t d omega. So if you have been asked to calculate x at x equals to 0 is what? 1 upon 2 pi minus infinite to infinite x of omega d omega. Right? If you have been asked to calculate the area, so this is what the area of your frequency domain signal, right? The area of a frequency domain signal is what? 2 pi times x of 0 is equals to area of the frequency transform of xt. The signal that you have got in the time frequency domain, the area of that signal is equals to what? 2 pi times x of 0. The value at the signal in time domain at t equals to 0 times 2 pi. Okay, or if you have to calculate the area in time domain, what will you do? You just have to calculate the Fourier transform and the value of Fourier transform at omega equals to 0. Is it making sense, you guys? Are you able to get it? Whatever we are discussing.
Yes, sir.
Okay. Now the next thing is, I told you x of t is what? X of omega. Now use the property e to the power minus e to the power j bt times xt. What will happen? What do you say? If you are multiplying something in the multiplying the complex in one domain, there will be a time shifting in the other domain. The shifting in the other domain, right? So what will happen here? X of omega minus b or plus b?
minus b.
Correct. X of minus b. Similarly, e to the power minus j bt times xt. So it will be x of omega plus b. If I'll just add both and divide it by 2, what will happen? E to the power minus j bt xt will be common plus e to the power j bt by 2 is what? X of omega minus b plus x of omega minus plus b by 2. This is what? This is which signal? Cos, cos bt. So for any signal that has been given to you, if you are multiplying cos in time domain, what will happen in that frequency domain? Frequency domain, the signal will get shifted left side and right side with frequency of b. Okay, so any signal that you are multiplying cos bt in the time domain, in the frequency domain, what will happen? This is what in the frequency domain it is getting shifted. Clear? Is this clear to everyone? Now just solve this question. Let's for example a signal has been given xt minus, now you have to calculate the area minus infinite to infinite dt. What will you get? What will be the value?
1 by
1 by,
only 1.
so what is the frequency? I told you the frequency transform of e to the power minus a omega t.
So it is
2a upon a square plus omega square. Correct? Right? And I told you, right, what is the area? If you have to calculate the area in time domain, what is the value? X of 0, right? You calculate the frequency domain. You can integrate it also, that is fine. But without integration also you can calculate. How will you calculate x0, right? X, I told you, right, x of omega is what? Minus infinite to infinite xt e to the power minus j omega naught t dt. Just put omega equals to 0. If you will put omega equals to 0, this will be 1. So basically you are calculating the area only. So this has been asked. Area of this signal. Area of this signal in time domain will be equals to what? In the frequency domain, whatever the frequency transform that you are getting, just put omega equals to 0. Here, this is the frequency transform of the signal. Here, a equals to 1. So, if you just put a equals to 1, what will happen? 2 times 1, 1 square plus omega square. Omega, you have to put it as 0. So, you'll be getting 2 as a area. So, it's pretty simple, right? Correct? Yeah. Now, you have been given a signal xt as e to the power minus t for t greater than 0 equals to 0. You have been asked to calculate 1 by 2 pi minus infinite to infinite x of omega d omega. What will you get? You will be getting x of 0. Correct? You already know x of t is what? 1 upon 2 pi minus infinite to infinite x of omega e to the power j omega t d omega. You just put t equals to 0. If you just put t equals to 0, you'll be getting this as 1. So you're left with 1 upon 2 pi integration of whatever the function, the Fourier transform that you have got, right, in omega domain minus infinite to infinite d omega. That will be what? X of 0. If you have been given x of 0, you just put t equals to 0. So you'll be having 1 as an answer. Correct? Right? Yeah. So next question I am giving, you just write it out. You have to calculate. You already know that for x, you know the Fourier transform as x omega. You have to calculate first shifting x of t minus td and then differentiation, then calculate the mode of this whole. Can somebody do it? Are you trying? Will you be able to do this? And how will you do this? Can somebody tell me? Are you guys trying? Can I speak out some names? Will you be able to do this? Anyone? Otherwise, I'll just speak out some name.
First, we have to calculate the time shift. So, in the frequency domain, x of t minus t naught is x of omega into e power minus j omega t naught. Then we have to apply the properties of differentiation.
Correct. So first you will do that shifting, and then for differentiation, what happens? You just multiply j omega. Correct, and the mode of this. This will be the answer. Pretty simple, right? Okay. Now we'll deal for the signum function. Can somebody calculate the Fourier transform of a signum function? See, I told you for a any energy signal you can directly use the formula to calculate the Fourier transform. For the other signals, you can so neither energy nor power you can't calculate for sure. But for the other signal, energy signal you can directly calculate the formula. For neither energy, neither power you can't calculate. Remaining signal you can try it out with the properties. You can calculate. See, for the signum function, how will you calculate? How do you write the signum function in the form of a with the help of ut? How do you write 2 of ut minus 1, right? You generally write it as like this. Correct? Now, if you will differentiate it, if you just want to differentiate it, what will you get? You generally get for this signal, you will be getting 2 of delta t. Now, if you will calculate the Fourier transform, if you want to calculate, what will you get? Fourier transform of this signal. So, Fourier transform of this signal is what? You will be getting what? For any signal xt, if you are differentiating, what happens? J omega times Fourier transform of signum function equals to Fourier transform of this delta function. What do you get? 2, right? So Fourier transform of signum function you will be getting as 2 upon this j omega will go here. So j omega. Okay, this is what you get. So for a signum function, the Fourier transform you get it as 2 upon j omega. Okay. Now the most important property that we'll be reading is the duality property. And this will help you to calculate the Fourier transform of many of the signals. See, the duality properties is for xt, if you have the Fourier transform as x omega, and now if you have to calculate the Fourier transform of x of t, this is not in omega. So for xt, you have already the Fourier transform as x omega. Now, similar function, same function in time domain, if you have been given, how will you calculate the Fourier transform of that signal? You can calculate you can use a formula, but without formula also you can calculate. So what you have to do, you just have to multiply 2 pi and then replace t with minus omega. Okay, so x of minus omega. So this is the duality property. If any signal that has been given in time domain, if you know the Fourier transform of that signal and the same signal, so here what is happening? You are just replacing omega with t. So any signal that is there in time domain, but same as the omega, like let's for example, for e to the power minus at ut, you have 1 upon a plus j omega. But if you have been given a signal 1 upon a plus jt, how will you calculate the Fourier transform of that signal? So you can calculate the Fourier transform of this signal also with the help of the duality property. Okay? Did you get the idea? So let's try to calculate. So now for e to the power minus at ut, I know the Fourier transform right? What is the Fourier transform? 1 upon a plus j omega. Now, if you have to calculate the Fourier transform of 1 upon a plus jt, what will happen? What will be the Fourier transform? 2 pi times this signal e to the power minus a times minus omega and u of minus omega. Is it clear to everyone? Duality properties, is this clear? Now, if it is clear, now you have to calculate for a sinc function. What will be the Fourier transform of a sinc function? You already know that for a rectangular function, what is the Fourier transform? A sinc function. Now I am asking you to calculate the Fourier transform of this signal, that is sinc function, in the time domain. What will be the Fourier transform? What do you have to do? 2 pi times rectangular function. What do we have to do? Replace t with minus omega. So, is this clear? Is this clear to everyone? Okay. So, what we have made conclusion, for a rectangular function, you will get a sinc function and the Fourier transform. Similarly, for a sinc function, you will get a rectangular signal in the Fourier transform, right? Okay, so for a rectangular function, you will get a sinc function, the Fourier transform, the time frequency domain. Similarly, for a sinc function, you will get a rectangular function in the frequency domain. Okay, so what happens for a rectangular function? You will be having a sinc function in the omega domain. Similarly, for a sinc function, you will be having a rectangular function in the time domain, frequency domain. Okay, this you should remember. And this generally is asked. Most of the gate paper generally deal with rectangular function and the sinc function only. Okay. Now let's for example see if you have been given to calculate the area of a sinc function. How will you calculate the area? See, earlier it was very difficult, right? A signal like this, how will you calculate the area? Now, with all these properties, right, you can calculate the area of a sinc function also. What will be the area for a sinc function? Can somebody tell me, calculate this? How will you calculate? Just tell me the approach.
The frequency domain, we will put omega equals 0.
Correct. So for a sinc function, you have to calculate for a sinc function to calculate the area in a time domain. What will happen in the frequency domain? You just have to calculate the frequency, like the signal in frequency domain, and just put omega equals to 0. Right? You already know that for a sinc function, what is the signal in the frequency? What is the Fourier transform of sinc function? Rect function, right? And what is this rect function? This from, let's for example, this can be from minus pi to pi in omega domain, right? And the value is what? 1. So at 0, what is the value? 1. So the area of a sinc function is how much? 1. So these are pretty simple, right? If you know this properties, you will be able to calculate the area. Otherwise, it was very difficult. Like it was very difficult to calculate the area of this sinc function. Okay, is this clear to everyone? Okay. Now calculate the Fourier transform of this signal 2a square plus t square. What will be the Fourier transform? So you already know that e to the power minus a omega t. What is the Fourier transform of this signal? 2a times a square plus omega square. Now use the duality properties. You have been asked for calculate 2a upon a square plus t square. So 2 pi times e to the power minus a, and just replace t with minus omega. Correct? Is this clear to everyone? Okay. Now calculate the Fourier transform of 1. What will you get? Just remember, use the duality property. For which signal you get Fourier transform as one delta function, right? So you know for delta function
2
you
pi
get
del
Fourier
of
transform as one, correct? Now if you have to calculate for one, you what can you do? 2 pi times del of minus omega. You already know that delta function is an even function, so 2 pi times del of omega. Clear? Now I have to calculate the Fourier transform of ut. For ut is what? Signum function upon 2 plus half. Correct? What is the Fourier transform of a signum function? 1 by 2. This is 1 by 2 times 1 upon this, sorry, 2 upon j omega, right? For a signum function. Similarly, for half, what will be the value? Half times 2 pi del omega. So you're getting how much? 1 upon j omega times plus del. So this is the Fourier transform of a ut. Any doubt? Anybody has? Anyone has any doubt? Is this clear, right? Everyone is able to understand this. Okay. Now, can you calculate the Fourier transform of cos of bt? How will you calculate? Just tell me the approach. See, how can you write the cos bt as e to the power jbt plus e to the power minus jbt by 2? You can write it like this, right? Okay, so now let's calculate the Fourier transform of this, Fourier transform of this, and then you can add it, right? So what will be the Fourier? So for one, we already know what is the Fourier transform? 2 pi times delta del of omega. With one, what I am multiplying? 1 times e to the power j bt. If I am multiplying anything, the complex j bt, what happens? What will happen? 2 pi times. So if you are multiplying any complex value in one domain, in the other domain, what happens? Shifting, correct? See, we have read here.
del of omega minus.
Yeah. So shifting in any domain, multiplication of complex exponential in the other domain. So we are multiplying a complex exponential. So in the other domain, there will be a shifting. So multiplying a complex exponential, the shifting will happen. So del of omega minus omega naught, omega minus b. If I am multiplying e to the power minus j bt, so here it will have 2 pi times del of omega times b. Just add first and 2 and divide it by 2. So e to the power jbt plus e to the power minus jbt by 2. So this will happen 2 pi times del of omega minus b plus 2 pi times del of omega plus b by 2. Right? So we'll be having del of omega minus b plus del of omega plus b. So for this cos of bt function, this is a Fourier transform. Clear to everyone? Is this clear, everyone? Okay. So I'll just go and then recap everything. So I hope all the properties we have dealt. I guess only the convolution we have not dealt. Convolution, okay, I'll just write that also. The convolution property. I hope you already know that. In the convolution we have read it about that, and basketball energy also. That also you already know that. What happens in the basketball? If you calculate, let's say example for xt, you have the frequency transform, like Fourier transform you already have. If you have been asked to calculate the energy, you calculate the energy, energy by xt dt, or you calculate this same as 1 upon 2 pi minus infinite to infinite x of omega del omega. You calculate it in time domain or in frequency domain, you'll get the same energy. Okay, and the last property is the convolution. So convolution property is nothing like if you have doing the convolution in time domain, in the omega domain or the frequency domain, what will happen? Just multiply it out. Okay, or if you are multiplying in one domain, you will get convolution in the other domain. Okay, is this clear? So this is also the Pascal energy. So this is also one of the properties. If you are calculating the energy in time domain or frequency domain, this is how generally you calculate it, and you will get the same energy. Okay, and the convolution property is also very simple. If you are doing the convolution in one domain, it will be multiplication in the other domain. I hope this is making sense to you guys. And we'll read about other things also, like the triangular function also. What is the you'll come to know that for a rectangular function we got the sinc function. Similarly, for the triangular function you'll be getting the sinc square function. Okay, that we'll read tomorrow. Okay, so I hope whatever I have dealt, is this clear to everyone? So I've just went through, like it maybe it was a bit faster, but you can just go through the recording again. But I have dealt with all the Fourier properties, like the Fourier transform properties. Okay, and the standard signals also, whatever the standard signal that we generally deal with, 5 6 signals, that also I have dealt with. So if you are just knowing this much, that will be sufficient for a Fourier transform. You just have to go and practice more and more questions. Tomorrow morning again we'll meet. We'll try to practice more questions. We'll try to solve some questions. Okay, and that will suffice the Fourier transform, I guess. Is there any doubt, anyone, that we have dealt today? Anybody has any doubt? I'll just upload this. Okay, so I'll just write it neatly, the Fourier transform ka whole things with the examples. You can just go through it. I'll just upload it after the session itself. Okay, whatever the slides that we have used, I'll just upload it here in the Google G space. Anyone has any doubt? Is it clear to everyone? Okay. Okay, then let's meet it tomorrow morning. Okay, we'll try to solve some problem from the Fourier transform. Okay, is it fine? Okay, let's meet it tomorrow, and go and I'll just upload the just now. I'll just share it in the Google G space. You just go through each and every problems. Okay, that will be more than sufficient. We'll try to solve some problem in the morning, and that will be it. Okay. Okay, and the morning Monday also we have a session. We'll be having a session in the morning. That will be a MATLAB session. Okay, a MATLAB session will happen because I can see that very less number of people are submitting the lab assignment. So we'll be having a session on Monday, and from 9 to 10, and again from 10 to 11, we'll be having a session interaction with the prof. Okay, you can just come up whatever the feedback that you have, and with respect to the quiz paper or anything, how is it going, the whole signal system, and what else we can do, or whatever, is it going fine or not, is it going with the same pace, is it the good pace or not. So you can just come up with your feedbacks, and then we can have a discussion with the prof. Okay, okay, then uh, thanks everyone for joining it up. I hope these sessions are helping you guys, okay, to understand the concepts. Okay, thanks and good night, have a good day.